Semiconductor diodes. Diode is a two-terminal PN junction device. This is the junction. This is a P type and this is N type. P type is having holes, N type is having electrons as majority carriers. Holes for P type, electrons for N type. Here also we'll be having electrons in P type and holes in N type, minority carriers. P type it is electrons, N type it is holes. Holes are positive charges and electrons are obviously negative. This diode or PN junction is made up of germanium silicon. It is represented in a symbol like this with the two terminals, anode and cathode, anode, and here is cathode. Diodes are two types, intrinsic and extrinsic. In intrinsic type PN junction diodes, the holes and the electrons are in balance stage. So number of holes equals to number of electrons. Due to that, they are poor in conduction at room temperature. Intrinsic conductivity of germanium is increased by 5% per 1 degree centigrade rise of the junction. The intrinsic conductivity of silicon increased by 7% per 1 degree centigrade rise in the temperature. Since intrinsic type PN junction diodes are poor in conduction, in which they are going to dope with impurities. The process of mixing and impurities in intrinsic diodes is known as doping. So after doping, they will become extrinsic diodes. N-type material is doped with antimony, arsenic, and phosphorus. P-type materials doped with boron, gallium, and indium. And this doping, the amount of impurities added in extremely small, that is 1 or 2 atoms of impurities for 10 to the power of 6 intrinsic atoms. The AC supply is given to a diode. Voltage across diode VD is my current I of diode. Then a positive supply is given to the anode. A positive and the majority particles in p-type are holes, which are positive charges. So positive and positive is going to reflect to each other. Then the holes moves toward the junction. Similarly, at the cathode, a negative supply is given and the electrons are negatively charged majority carriers in n-type. So they reflect each other. Now the electrons tries to move towards the junction. Then this junction or depletion layer of the junction is going to reduce and it starts conducting as soon as it reaches a particular value known as threshold voltage. Let this be VT, threshold voltage. Before that, there is a small amount of current here. This is known as threshold voltage or cutting voltage or turn on voltage of the diode. Then after the current starts rising, this is our IV. This is a forward biased region. ID is given by IS e to the power of VD divided by N VT minus 1. For germanium, VT is equals to 0.3 volts. Whereas for silicon, this VT is equals to 0.7 volts. Here in this ID is the current through the diode in amps. Then Is is the leakage current. Is value is typically around microamps to picoamps. Vd is the diode voltage with anode positive with respect to the cathode. N is the emission coefficient or ideality factor. Ideality factor for germanium equals to 1, for silicon it is 2. In practical case, it will be between 1.1 to 1.8. Vt is thermal voltage given by Vt equals to Kt by Q. So Q is electronic charge, value is 1.6022 into 10 to the power minus 19 coulombs. The P is absolute temperature in Kelvin. So K equals to 273 plus a degree centigrade. K is Boltzmann's constant, and this value is 1.3806 multiplied by 10 to the power of minus 23 joules per Kelvin. So from the formula we can say as the temperature of the junction increases, Vt also increases. When this Vt increases, Id also increases. The leakage current will be. This is going to continue until it reaches breakdown voltage, that is VBD. And this value of VBD, the breakdown voltage, is approximately 1000 volts. After that, still if you increase the reverse voltage, then the current is going to increase rapidly. The region after this breakdown voltage is known as a breakdown region. This region is known as reverse bias region. After operation of the diode, the Vd value must be below this VBD. So it's going to oscillate in between these 2 points. These are the VI characteristics of a diode. Reverse leaking current is minus 1.57 nanoamps. In a supply to a diode. Now I want to draw the forms for this. Vs and this is my Vd. Vs is a sinusoidal wave. As the positive charge increases, the A is more positive than the K. The conduction starts after Vt. Until that will be very less. So it starts conduction, follows the input voltage. Then at here it's not going to conduct, but reverse leakage current, it's not going to stop at this point. It will come to very less point, then it stops and stays continuous. It's positive, it starts conducting. Try to concentrate on this part. Draw a waveform for this. So this is the forward current of the diode, and then it starts coming to 0. After reaching that 0, it's not going to stop there. Then goes to some negative peak. This is I. Reverse recovery, let it be. This is the peak value. From here it starts going back. This point be 25% of IRR. Then from this point that reaches 0 to this 25%, it is known as the time T. So TRR, reverse recovery time, is this. And this is again divided into 2 parts, that 0 to peak of IR is TA, and P to 25% it is TB. TA plus TB is equals to TRR. This is reverse recovery time. TA is due to the charges at junction, and TB is due to the charges inside the semiconductor diode, and this is caused due to the minority charges. So this is our forward bias region, and this is our reverse bias region. TB by TA is softness factor. Reverse recovery time and softness factor is having an important role in choosing a diode for the particular application.